and applications. So the main goal of this section, because that line's not straight, is to solve what we call literal equations, which is essentially when we have a formula. So there's formulas all over the place in science and business and everywhere else. Formulas are just equations that have more than one variable in them, so you can like plug in several things and then solve for whatever it is that you want. When we solve literal equations, we've done this before actually, when we did lines and we had like 2x plus 5y equals 8. If we solve this for y, like get y by itself, we've really solved a literal equation, because a literal equation is any equation that has more than one variable in it, but when you solve it, you treat everything except the variable you're solving for as if it's just a number, like as if it's just a number you know. So if we were to solve this for y, if x was just some number, then 2x would be just some number. So the first thing I'd have to do is subtract it, right? And then divide both sides by 5. And when we were actually working with linear equations, we found that it made a little bit more sense to write it as 8/5 over 2/5 x, just so we have like the m and the b separate terms. So that's the basic idea, is we're going to use the same process that we use to solve any other equation. We're just not going to get an answer that's a number. We're going to get an answer that's an expression. So sometimes when you're out in the world and you have some relationship between variables, maybe it's not solved for the variable you want. And so if we solve the equation for one of the variables before we put any numbers in, we can do things like program it into Excel and then change the numbers a billion times without having to solve for it every single time. So it can be pretty handy to just, all we're doing is rearranging the formula so that it outputs what we want to get from it. So this one wasn't too bad. They get a little bit clunkier. So let's just do a bunch of these. Like I said, the process for solving is exactly the same as solving a linear equation. We're not doing any quadratics yet. But we just have a lot more letters than numbers. So let's solve 703 W over H squared equals I for W. So when it says like solve for W or solve this for W, all they're telling you is which one of the variables you want to isolate. So if there's all these variables in there, we don't know which one we want to solve for unless we're told. So in the problem, it'll tell you which variable you want to isolate. We always try to do like actual formulas. This is the BMI formula. Anybody wants to calculate their BMI? So W is the weight, and then H is your height in inches. And if you plug it into that formula, the I represents your BMI. So we're going to solve this for W. So if we knew somebody's BMI and we knew somebody's height, we could solve for their weight if we didn't have a scale. So when we solve linear equations, let's just remind ourselves of the steps. So first of all, the variable you're solving for. Is treated like the only variable. in the equation. So what we mean there is like, when we solve linear equations, we get all terms containing our variable on one side and all constant terms on the other. When you have like 3 variables, that could be a little confusing because what are the terms that contain your variable? So we just make the generalization that every number is like a known value other than the one we're solving for. So in this case, if we were going to get all the terms that contain our variable on one side, that would just be the terms that contain w, because that's the one we're solving for. And that can change. Like, I could give you a formula that has 5 variables in it, and I can ask you to solve for every single one of them, like in separate problems. And so there, it's not like there's like a variable that it's right to solve for or anything. It's just the process of isolating one of them. So we always clear fractions first. And just like we did yesterday, we will do that by multiplying both sides by, I'm not use red today, let's do, it's pretty purple. The LCM over 1. We don't have to worry about restricted values here, because we're not actually getting a value for our variable. So when we solve for w, we're not going to get like w equals 9 or w equals whatever. So since we're not ending up with something that w is supposed to be equal to, we have nothing to compare to our restricted values anyway. So they don't really serve a purpose here because we're not actually solving for a number. We're just rearranging the formula. So we will multiply both sides by h squared. So we have h squared over 1 times 703w over h squared equals h squared times I. Be careful with i's. They look a lot like 1s. In these problems, you're not usually going to get like a polynomial like the ones we saw yesterday in the denominator. Usually it's just going to be like 1 or 2 factors, like monomials. And so in general, if there's one fraction, just multiply it by whatever the denominator is. If there's 2 fractions, on almost all of these, they're just different, and you can multiply by all of the denominators to clear fractions. So sometimes it's just like a bunch of them, like x, y, z would be your LCM. Here we're going to cancel our h squared, and we get 703w equals h squared times I. So after clearing fractions, again, we're not solving quadratics. This has an exponent, but it's not on our variable. Remember, w is our only variable, so because there's not an exponent on our variable, that h squared is just some number. So we don't have to think of this as a polynomial equation. We can still think of it as linear because there's no exponent on the w. So because it's linear, and these always will be for now, you're going to get all terms containing the variable on one side and all constant terms. I'll put it in quotes. I only put it in quotes because nothing's actually a constant term here, right? There's all those other variables. We're just thinking of them as constants. Again, these are exactly the same steps we always use to solve linear equations. Sometimes it's just nice to actually see them when the equation starts to look a little bit different, to remind yourself of exactly what you're doing, because it kind of gets automatic when we get used to solving x over and over. So once we do that, we are going to factor out the variable. If necessary. In this case, it is not necessary. I just want it to be here so we have all the steps. We will do it in the next problem. That occurs when you have more than one term containing your variable. So you have to factor that out, and we'll see that in another example. And then the last thing is just to isolate the variable. Which we do. Stupid watermark. Which we do just by dividing both sides by anything our variable is being multiplied by. So in this case, on the left side, w is being multiplied by 703. So to isolate w, I'm just going to divide both sides by 703. So we end up with w equals h squared I over 703. Does that make anybody else think of Hawaii and really wish you were there? So warm. Questions? Does that make sense? It's not too bad as long as you don't let yourself get overwhelmed by it. Like sometimes you can look at them and it looks pretty confusing. But again, if you just follow that same procedure that we use when we solve equations with numbers. And one thing you can do is, like, if all else fails, like if you really blank and you don't know what to do, you can write an equation that's similar but with numbers and like ask yourself what steps you would follow to solve it. So like if I wanted to solve A equals 5/2 times B minus C for, what did I say, B, and I like all of a sudden panicked and I blanked and I'm like, I'm really not sure what to do. You could just say, okay, I'm going to put numbers in for everything but B. I'm just going to like make something up. So like 6 equals 5/2 times B minus 3. I'm going to make it 4. And then I'd ask myself what I would do, right? So the first step to solving that equation, when we look at it, like that looks like a fairly simple equation, right? Would be like to distribute the 5/2. And so that means that the first step over here is also to distribute the 5/2. But sometimes just seeing it in like concrete terms can help just jog our memory a little bit. So we have A equals 5/2 B minus 5/2 C. And so like same deal over here. And then if I'm still in a panic, I can be like, oh, okay, well, I just add 10 to both sides, right, if I was over there. And so here, this is the piece. It looks different, but that's the term that is in the same place as that 10, right? So our next step is just to add 5/2 C to both sides. So A plus 5/2 C equals 5/2 B. And really at any point in this process, you could clear fractions, like you could do that right away. The only reason I didn't here, I guess, was just because I had one fraction, it was numerical, and I felt comfortable kind of just like working with it. If you would rather not work with the 5/2, you can certainly multiply both sides by 2, like right off the bat, just to get rid of that numerator or that denominator. Because in reality, we're going to have to do something like we're going to have to multiply by the 2 in order to isolate B anyway. So we have all terms containing B on one side. We have all terms not containing b on the other side. So there's a couple things you could do here. You could clear fractions first and then divide both sides by b or by 5. Or you could multiply both sides by the reciprocal if that's something that you're comfortable doing. We haven't done much of that, but if it's something that you already know and you're comfortable with it, that's totally fine. I'm going to just do it the way we've done it so that we're not looking at something completely different. So I'm going to multiply both sides by 2. So that's 2a plus 2 over 1 times 5 halves c equals 2 over 1 times 5 halves b plus 5c equals 5b. And like I said, you could have done that back at the beginning if you wanted to. Just remember that we did a few of these at the very beginning of the course when we were solving all those linear equations. Remember that if you were to take this guy and multiply both sides by 2, it would be like that. So you end up just multiplying this by 2 because this part is not a separate term. It's not being added or subtracted to anything. So that whole thing is one term. So I just multiply it by 2 once. I don't like distribute it. So what should I do now? Yeah, we're just going to divide both sides by 5 to isolate b. Probably the most common thing that we see is when people struggle with this is like when you guys solve an equation that just has one variable in it, like I said, like you've sort of internalized that process, so you can kind of just look at it and kind of automatically do what you're supposed to do. With these, because there's more than one variable, it's easy to kind of look at it and just automatically do something, like add or subtract something from both sides. And I sometimes see people start to like move things back and forth because they haven't gotten a really concrete idea of like what they need on one side and what they need on the other. And so that's why like I wrote down those steps. If you didn't write them down, feel free to take a picture. So that like instead of getting into that like back and forth, you can kind of just stop and be like, oh yeah, I need to get all the terms containing W on one side and all the terms without a W on the other. So just to like remind yourself of exactly what your goal is there. Let's see, what should we do next? Yes?
So we can leave it as 5c over 5?
Oh, great question. So remember that this is all one factor.
But if you multiply by the reciprocal,
Mm-hmm.
would that only be 2/5 a minus or plus c?
If we multiplied, so if we did it right here. Yes. So, like, because you're saying that it would be 2/5 a plus c equals b.
In the beginning.
Uh-huh.
Oh, a equals 5
Yep.
halves.
Uh-huh.
So every time I multiply by the reciprocal,
Mm-hmm.
so it would end up being 2/5 a equals b minus c.
Mm-hmm.
So we add c, so then it would. That's why I'm confused.
Great question.
Yeah.
So if we look at it in this way, if we go like this, we end up with 2a plus c equals b, which also isn't what we think it should be, right? So we can't cancel that 5 because it's part of a term and not a factor of its own. However, if we go back to how we, remember when we had linear equations and we solved for y, how we split it into 2 terms? So we kind of distributed the division just like we can with multiplication. So we could do that same thing here and say this is 2a over 5 plus 5c over 5 equals b. And now because I've split it into separate fractions, 5 is a factor of that second numerator. So I can cancel it. And so you'd get your 2/5 A plus C, that you were right. It should be. I'm fine if you leave it like this. I'm also fine if you do that. So for the most part, I will take any answer which is equivalent to the answer I got, with one exception. You're like, you'll get your variable on one side. The other side shouldn't be a complex fraction. So if you get a fraction that has a fraction in it, I will expect you to simplify that to a single fraction. But other than that, like, because there's different approaches, like in orders you can kind of do this in, like we saw we could clear fractions up here or down here. Sometimes the answers don't look exactly the same, but as long as it's equivalent, that's fine. Thanks, that's a great question. Any others on this one? Okay, let's do, oh, it's the simple interest formula. When I was in high school and they taught us the simple interest formula, they made it seem like it was this super big, like, adulting deal. And then I became an adult and realized that nobody anywhere ever uses simple interest. They use compound interest, and so all that stuff they taught us is, like, completely useless. We'll do the compound interest formula in much more detail later in the semester when we do exponential functions, but we want to solve this guy for P. So our goal is to get P by itself. The thing that presents a problem is that I have more than one term that contains P, right? And like, you have to be a little bit careful with these problems because it can be easy to be like, oh, well, hey, if I subtracted PRT from both sides, that would get P alone, which is true, it would. However, imagine plugging numbers in so that you can find out what P is. In order to figure out what P is, you would have to know what P is, right? Because P is in the right side as well. So there'd be no way to actually figure it out. If you knew A, R, and T, you still don't know P because you can't actually plug all the numbers into the right side to get the left. So that's not going to work. Now, when we're working with numbers, like if I had the equation 10 equals 5x plus 3x, what do you do there?
Combine the x's.
Right, you combine like terms, right? And we do this in our head all the time. And so we don't really think about what we're doing when we do it. But when you combine like terms, it's actually factoring out a GCF. You're saying that if I undistribute an x, I end up with 5 plus 3 times that common factor of x, right? And that's how we get the 8x. I mean, we don't actually do it that way, but that's why it works to just add the 5 and the 3. So we can do the same thing up here. We can factor out a p, because then we'll just have a single factor of p, just like over here we ended up with a single factor of x. So we have A equals P times 1 plus RT. Remember that one again, just like with polynomials, the number of terms inside the parentheses needs to be the same as the number of terms you started with before you took out a GCF. So you put that 1 in there as a placeholder. And so now we're just going to divide both sides by whatever P is being multiplied by. So we don't have to worry if we have P times something in parentheses. We don't have to worry about what's in the parentheses or how messy or not messy it may be. You're just going to divide by the whole thing. So we end up with A over 1 plus RT equals P. Good stuff. Okay, let's take it up like a tiny little bit. Let's solve. Solve for C given 5C plus 12 equals CA over X. So you'll notice I've worded each problem slightly differently. I'm trying to kind of cover all the bases of how you might see it. There's different ways of asking the same exact question. So the wording's a little different. We're saying the same thing, just solve the formula for C. So first thing I should do is clear a fraction. So I'm going to multiply both sides by X. So we've got X times 5, whoa, it's not the right one, 5C plus X times 12 equals X over 1 times CA over X. So my X will cancel on the right side, and we end up with 5CX plus 12X equals CA. The order you put your variables in doesn't matter. We often put them in alphabetical order, although I noticed when we were doing the difference quotient that I have never put that middle term when I multiply x plus h by x plus h. I've never put that in alphabetical order in my entire life, even though I think I put them all in alphabetical order. I just realized that yesterday. Kind of freaked me out. But I don't care the order that you put, within each term, I don't care what the order is of the variables, but definitely put the coefficient in front. So you always want that number in front. So that it doesn't kind of get mucked up and feel like an exponent or something else weird. Now, what do we want to do? So what's the next step in our list of steps?
Get C on the same side.
Yeah, we're solving for C, so we want to get all terms containing C on one side. So here I'm going to have to subtract 5CX from both sides. So 12x equals CA minus 5CX. And when they can contain x, it can be kind of tricky because we're really used to solving for x. So just kind of keep referring back to what your variable actually is. What do you want to do next?
Factor out the C.
Yeah, we'll factor out the C. So at this point, this is exactly like the problem we just did once we get all the terms containing C on one side. So we're going to write 12x equals C times A minus 5x. And then divide both sides by A minus 5x. So 12 over A minus 5x. Just since we're looking at it and we just talked about it, division, like in this problem, we talked about how we could divide each term on top by 5 if we wanted to. The same is not true when the addition or subtraction is in the denominator. This is not the same as 12 divided by A minus 12 divided by 5x. So if there's addition, subtraction in the denominator, like you just can't do anything about it. Like you can't split that up as addition and subtraction. And then, oh, I should say equals C.
Isn't it 12x?
It sure is. Thank you. And also we can't cancel the x, right, because of that subtraction between the a and the 5x. So one last little tip about these is even though like when I clear fractions, I always multiply the LCM by each term individually. But for some reason, it seems like when we get to these particular problems, people like to do like, I'm going to multiply by x on, well, usually what happens is they're like, oh, I'm going to multiply by x here, and I'm going to multiply by x here, which is fine. Like, it doesn't cause any problems, except that the way that I just wrote it didn't actually multiply x by the entire left side. You guys see that? So you can do that, but like so many other problems, you need parentheses if that's the choice you're going to make. So if you're just going to write that x once, you got to put the entire left side in parentheses.
Let's
And
say the numerator was like 2a minus 10x. Could you distribute out and then cancel out the...
you can factor out your GCF and cancel, yeah.
Even if it is
Mhm.
subtraction on the bottom, as long as like they're both in parentheses.
If they were both, if when you factored the numerator, one of your factors was a minus 5x, then you'd be able to cancel. So these, like as far as fractions go, it's going to work the same way as all the other ones we've done. Again, it just looks a little different because there's more variables. Let's talk about boxes. This is the fun stuff because you get to practice drawing three-dimensional boxes. Isn't that your favorite pastime? Like when I was a kid, like in high school, like I draw boxes all over. Didn't you do that? Doodle the box. Yeah. So now you get to see if you still remember.
They're always lopsided. I hate
Okay, so the first one we're going to do is we're going to say a fully enclosed rectangular box has volume V equals length times width times height. We want to assign variables to our unknowns and solve for H. So this is the formula for the volume of a box. It is always the formula for the volume of a box. The way you can think about it is like it's just the bottom of the box multiplied by the height. So like if you can remember the area of a rectangle formula and use that on the bottom of the box, then you just like build it up like a three-dimensional printer does, like its whole entire height. So you just multiply that by its height. Does everybody know that formula? Like if it wasn't on the test, would that seriously inhibit your ability to do a problem about volume? Or we feel pretty good about length times width times height? So let's draw a picture because it's fun. No, because that way we can assign our variables. Okay, so when we assign variables, we had a problem similar to this on one of the homeworks, and I often saw like all the sides, like all the edges labeled, which you don't need to do because we're not trying to find like the length of all this. Like it's not like one of those fence problems where we're going to add up the length of all the edges. There's one height, there's one length, and there's one width, in the sense that the dimension width is a property that the box has, and it doesn't really matter how many places it occurs in the box. So our width, we'll say, is this guy right here. And we'll call that W. And then our length is going to be this guy. We'll call that L. And then our height, we'll call H. So when we do length times width times height, even though like there's like 4 edges that are H units long, we don't do like H times H times H times H, or like 4H. Just like with a rectangle, when you find the area of a rectangle, you just do like width times length, right? Even though there's like 2 sides that have that width and 2 sides that have that length. So our volume is going to be V equals HLW, which if you wrote LWH is totally fine. Order doesn't matter. How should I solve that for H? I promise it's not a trick question. Yeah, we're going to divide both sides by LW, right? Even though it's not in parentheses. And the reason it's not in parentheses is, unlike the other problems that we were just doing, there's no addition or subtraction there, so we don't need to group it with parentheses. But the same idea applies. At this point in solving a literal equation, you just divide both sides by whatever H is being multiplied by. So like whatever, if at this point you should have, I mean in this we only had a multiplication anyway, but in any equation at this point you would have only multiplication on that side, and so you just divide by whatever it's multiplied by. So we have V over LW equals H. Okay, let's do another one. This one's even more fun. So an open topped box. Oh, it's rectangular box. Has length L and width W. Its height is 2 less than 5. I'm supposed to write that in words. 5 times its width. We're going to write a formula for surface area. And solve it for L. So let's draw another picture. Oh, that got wobbly. And then we'll label. So what they give us variables for are the length and the width. So we've got our width, we've got our length, and then we have our height, which we can't label H because we have information about how to represent our height in terms of our width. So we don't get another variable here, because if we put an H there, then we wouldn't be reflecting that relationship. So the height is 2 less than 5 times the width. So 5 times the width is 5W. And 2 less than that I get by subtracting 2. Now we want surface area, this time not volume. So one of the things when you like do geometry classes and such, there's a lot of formulas and it kind of feels like you have to memorize them all. But some of them, like, you can always just kind of build on your own. Surface area is one of those. Like, surface area is just the area of the surface of the box. So like the sides and the bottom in this case, because it was an open top box, there's no like cardboard on the box or on the top. So if you were to cut on all the edges and like open it, then the area of that flat piece would be the surface area. So to find the surface area of a 3-dimensional figure, you just want to break it down into sides, which are all 2-dimensional, and then find the surface area of each of, or the area of each of those, and just add them all together. So we're going to add the area of the bottom to the area of the left and right side to the area of the front and back, which are all just rectangles. So we get them by doing what? Length times width, which, not the length and width of this, but the general statement, length times width of a rectangle. So our surface area, if you're really disturbed by the fact that there is no S in that, you can put a little subscript right here. If you call it AS, that's like 2 variables. It's like A times S, and that can get tricky. Like, you can't treat AS like a single variable. I mean SA. But you can also just call it A. So this is going to be the bottom plus left and right plus front and back. I'm grouping left and right and front and back because they're the same. Like, the area of the front is the same as the area of the back. So once I find one of them, I can just double it. And same with the left and right side. So what is the area of the bottom of my box? WL, right? The dimensions of the bottom. And you really kind of have to draw a picture for these because you kind of have to visualize all the rectangles. The dimensions of the bottom are W by L. So the area is WL. And then let's look at the left or the right side, and then we'll just double it for the left. So one dimension is right here, and then the other dimension is right here. And that's the rectangle on the right side of my box. Does everybody see it? So what's the area of that right side? So L times 5W minus 2. If we express a single length or width or whatever with an expression, it has to go in parentheses when we put it into a formula, because we're thinking of it as a single number. Like, that height is just one number. It just happens to be written funny. And then we're going to double that to account for the left side as well. So I've got 3 sides so far. I have the bottom, and then I built up these 2 sides, and now I need to build up the front and the back. So front and back, I've got this guy right here, and then this guy right here as my dimensions. So what's the area of just the front? W times 5W minus 2. That's the area of just the front, and then we have to multiply that by 2 to account for the back. So now we've gotten all 5 sides, right? We have the bottom, 2 on these sides, 2 on these sides, and that's all of our sides because there's no top, right? If there had been a top, if it was like an enclosed box, we just would have doubled the one for the base, the WL. And now we're supposed to solve for L, and we can do this in 2 minutes for sure. We're going to distribute first. 10LW minus 4L plus 10W squared minus 4W. I have one pair of like terms that I might as well combine. So I have 11WL minus 4L plus 10W squared minus 4W. We're solving for L, so all the terms that contain L are on the right side already. So all I have to do is get all the terms that don't contain L on the left side. So we'll leave those first 2 terms alone, and we're going to subtract 10W squared, and then we're going to add 4W. So we have A minus 10W squared plus 4W equals 11WL minus 4L. So now we've got all constant terms on the left, all terms that contain L on the right, so we can factor out an L. And we have this whole mess. Equals L times 11W minus 4. And only one more step, which is to divide both sides by 11W minus 4. So L is equal to A minus 10W squared plus 4W over 11W minus 4. There's addition, or there's subtraction down here, there's addition and subtraction up there, so that's all grouped. I can't cancel anything. So this is one of these problems, and there's a lot like it, that it looks really complex. I mean, we wrote a lot of stuff, but like, did you notice how the process to solve for L was really like the same, even though we had all that stuff that looked messy going on? So if you can just like remember that process, instead of getting overwhelmed by all the stuff you can see, then it always works. So tonight you have no My Math Lab, which means that over the weekend